I've just recorded 3 videos that take longer than I really want to commit you to, although you might well need to go through those videos as I recorded them. But if some of you might not, and if you don't need to spend a half hour on 3 videos, we'll try to go through this one in 10 minutes or less. Okay, that's summarizing the 3. So we're looking at stopping distance versus speed. If a car is traveling along, the faster it's going, the longer it takes it to stop. So stopping distance from the time you hit the brakes is average speed multiplied by the time to stop. So if you average 5 meters per second and it takes you 3 seconds to stop, or then multiplying 5 meters per second by 3 seconds gives you 15 meters that it takes to stop. Okay, that's probably not going to take you 5 seconds to stop from 3 meters per second. 3 meters per second is just a moderate jog speed, so you'd stop much quicker than that in a car. In any case, the time it requires you to stop is given by the speed divided by the acceleration, the magnitude of the acceleration. And I'm not being real rigorous about the physics here. The acceleration that you can get in a car on good pavement with good tires is 6 meters per second squared. If you divide that into the speed in meters per second, the meters per second divided by meters per second squared gives you the time to stop in seconds. And if you do the algebra of the units, you can find that. I'm going to suppress the analysis of the units, although that goes against my nature, and just say, okay, we have this formula for the time to stop. It's going to be 1/6 v, where v is the speed, and the time to stop will be t in seconds, and we'll use a capital T for the time to stop. So if the time's in seconds and the speed's in meters per second, this speed in meters per second will give you the time to stop in seconds. Now we could graph T versus V, and it's always good to have a graph. In order to do that, let's use the formula to make a table, and you should pause and make your own table without looking at this one. But in any case, using velocities, the convenient velocities 0, 6, 12, 18, 24, we get the time to stop being 0, 1, 2, 3, 4 seconds. We can graph those points, 6 meters per second, 1 second, and I should probably label this 1, 2, 3, 4, and we get the points on the graph corresponding to the table, and we get this graph of the time to stop. Now this is the time to stop from the time you hit the brakes. We'll worry about the time it takes you to hit the brakes once you realize you have to stop in a minute, but let's just get this model. Okay, now if we multiply the average speed, we're going to multiply the average speed multiplied by the time to stop. Here's the time to stop given our velocity. What's our average speed given our speed when we hit the brakes? Well, our speed is going to fall from whatever our speed is to 0 as we stop. The average speed then would be the average of our initial and final speeds. Our initial speed is the speed that we're traveling when we begin the stop. 0 is the speed we're traveling when we stop, and we average those two, we get v over 2, so that our formula for the stopping distance, or our result for the stopping distance, it's going to be average speed times the time to stop. Average speed is v over 2, time to stop is 1/6 v. We multiply those, we get the quadratic expression v squared over 12. Multiplying average speed by time to stop gives us the distance to the stop. Also noted up here that a meter per second is about 2.3 miles an hour, so this 24 meters per second is going to be somewhere around 55 miles an hour. Continuing our analysis, we have our distance is 1/12 v squared, obtained as we saw, and that's from the time you hit the brakes. Now, if we assume a reaction time of 1/2 second before you hit the brakes, you're going to still travel at velocity v for 1/2 second. How far do you travel in 1/2 second at velocity v? Worth stopping and thinking about that before you look at the answer, but the speed is v, the time is 1/2 second, so the distance in meters, well, the distance is v times 1/2 second, And we're going to represent that as 1/2 v, assuming that v is in meters per second, t is in seconds. So what's our total stopping distance? Well, that's going to be the 1/2 v squared that it takes to stop from the time we hit the brakes, added to the 1/2 v, the distance we move before we hit the brakes, giving us the quadratic function d of v, distance as a function of speed, is 1/2 v plus 1/12 v squared. We recognize this as a quadratic function. It's in the form av squared plus bv plus c. Our zeros of this function are solutions to the equation. I'll set this equal to 0. That's how we get the zeros of a function. This can be solved by factoring or by the quadratic formula. Now, I'm not going to go through the details of that. We went through that in the preceding videos, and you should be well familiar with those procedures by now. Okay, but what do we do to analyze this function? Well, we find the zeros by factoring of the quadratic formula, and in this case, factoring is going to work just fine. We find the axis of symmetry for the graph, and we find the vertex. Okay, well, it turns out the zeros are at v equals 0 and v equals -6. Factor the v out, factor 1/2 v out, and we find that v equals 0 and v equals -6 are our solutions. Now, v equals -6 is a point on the graph of this function, but it's meaningless because v is our speed. Velocity is how fast we're going and in what direction. Speed is just how fast we're going. And how fast we're going can't be less than 0. We can't go at a negative speed. We can go at a negative velocity, meaning our velocity, we have a speed in the direction opposite whatever direction we regard as positive, but we can't have a negative speed. Still, if we want to graph this function and get an idea how the graph works, we'll want to include these points on our graph, but we're going to want to indicate somehow that this isn't a real result. This isn't a result we could get in the real world. Okay, so anyhow, our quadratic function has parameters. What? A is 1/12, B is 1/12, 1/2, C is 0. We can get the vertex, -b over 2a comes out -3. Or we could just say the vertex is halfway between our zeros at 0 and -6, and halfway between those is at -3. So if we do our graph, we have a 0 here at v equals 0, a 0 at v equals -6, and an axis of symmetry at v equals -3. I haven't labeled that, but it's going to be at v equals -3, halfway between the two zeros. We plug -3 into our function, and unless I've made a mistake, the result is -3/4, so that our vertex will be at -3, -3/4. -3/4 isn't a stopping distance. We can't stop in a negative distance. We have to stop in a positive distance. But again, these points that don't correspond to reality are still important for understanding our graph. Now we pose the question, what's the stopping distance at a velocity of 30 meters per second? And what's the maximum speed at which we could stop within 100 meters? To find our stopping distance at 30 meters per second, d of v tells us the distance it takes to stop at velocity v. So as long as our velocity is in meters per second, our distance will be in meters. We just find d of 30, plugging 30 in for v. And when we do that, I won't go through the arithmetic of it, we get 90, meaning it takes 90 meters to stop at 30 meters per second. I'll note that 30 meters per second is right at around 70 miles an hour, common speed limit on the interstate, which nobody ever breaks. Okay, maximum speed to stop within 100 meters. That's a little more involved. Okay, it's d that's equal to 100 meters, and we want to find v. Well, what do? We set d of v equal to 100 meters. So that means we're going to set 1/2 v plus 1/2 v squared equal to 100 meters. We do that in this equation and solve for v. What kind of an equation is this? It's a quadratic equation. It involves d and v squared and a constant. We put this equation into standard form by subtracting 100 from both sides. and we get this form, and our parameters of the quadratic are then a equals 1/12, b equals 1/2, c equals negative 100. Now, if I was really solving this and not wanting to just illustrate a little bit of fraction arithmetic, I would have multiplied everything by 12, and that would have simplified this equation by putting everything into integer form so we don't have any fractions. And you might want to do that. You really ought to solve this equation both ways. Using the fractions, it's going to be messy. We substitute 1/2 in for b here and here. We substitute 1/12 and negative 100 for a and c. That gives us negative 4ac, 4 times 1/12 times negative 100. And our denominator 2a, 2 times 1/12. Simplifying a little bit, we get this. Multiplying through, dividing by 1/6 is the same as multiplying by 6, so we change this form to this form, and in the process we put everything under the radical over common denominator so we can add it, and then we add those. We get 403 over 12. We factor out a 1/4, leaving us 403 over 3. Square root of 1/4 is 1/2. We get this form. 403 over 3 is 134 1/3. 134 is a little closer to 144, the square of 12, than it is to 121, the square root of 11. So this number is going to be somewhere between 11 and 12. Half of that's going to be 6 or a little less than 6. Using that arithmetic, we can do the 1/2 and so forth, but I believe we get 31 or negative 37. We reject negative 37. Speed can't be negative. Our conclusion is that the stopping distance is about 31 meters per second. Now, this is all done in more detail on 3 preceding videos, but when I put these in order on the web and in the email, this will precede the 3. So if you look at the next, if you're doing these in the order I've got them presented, the next 3 videos expand on this in case you need to see more detail and have any trouble understanding this.